Thank you, Pooja, also for organizing this. Really looking forward to all the presentations today. And I really think it's an honor to be invited here today. Now I can present to you our latest work at FICO in the area of combining machine learning and human expertise. Now, a few words briefly to introduce FICO, also known as Fair Isaac. The company has been pioneering commercial credit scoring back in the 50s. And today we are serving our clients, businesses worldwide, to make better decisions on their customers with our software, both predictive analytics and optimization. And these decisions span all kinds of areas from risk, fraud, marketing, collections, across the entire customer life cycle. That means our software affects millions and millions of customer decisions, operational decisions, and probably billions of transactions, decisions on transactions like authorizations and so on. So a lot goes on behind the scenes. It's based on the FICO algorithms and FICO software. The goal for today is to leverage the latest and greatest algorithms that come from machine learning to develop superior predictive models, or scorecards as we often use them, that leverage all the machine learning that we can get from the data, get all the signal from the data. But at the same time, at FICO, we always realize that in the end of the day, what really matters is not making better predictions, but making better decisions. And becoming able to implement these systems in the real world takes, in our experience, a whole lot more than just machine learning. So it really means we need to balance machine learning results with human expertise. That opens up the questions, what are the effective ways to combine learning from data, data-driven learning, with human judgment and domain expertise? So this is what I want to talk about today. Now, a little bit more about motivation here. Why should we balance judgment, domain expertise, with data-driven modeling, with the signal from the data? A prime use case, that's probably the easiest to explain, is credit scoring. So that goes back to our roots. There are lots of regulations in the area of credit scoring. For example, the Equal Credit Opportunity Act prescribes for lenders that they don't use protected characteristics. An example of a protected characteristic that's not an easy one is age. You can use age of a credit applicant, but you cannot use it in a way that discriminates against older applicants. And another example is lenders in the US need to give reasons if they decline an applicant for credit. So for example, they could say, Gerald, your debt to income ratio is too high. And I would probably understand that. Or they couldn't say, hey, Gerald, your debt to income ratio is too low. If you increase it, we're going to accept you. That would be a bad reason. So now if you build a data-driven model, you could end up with adverse action reasons that don't make any sense, or you could end up violating the monotonicity restriction on age. So these are a few use cases that are easy to see, and that's kind of the FICO culture came from credit scoring. That's why we have always seen learning from data as just one side of the coin, and the other side of the coin was to impose business constraints and expertise on these scoring models. However, infusing expertise into predictive models has far more applications than just credit scoring. For example, data usually drifts over time. So you could find yourself developing a model on a training data set that's not fully representative for the future, and your model will need to extrapolate somewhat in the future. Statisticians know that extrapolation is dangerous. You don't want to leave extrapolation to the whims of a data-driven model that extrapolates in uncontrolled fashion, but you want to put judgment on the extrapolation. Another use case is that your development data sample may be biased. There may be a selection bias that may depend on some variables that are responsible for the selection that you may not even have measured. And in those cases, your only hope is to impose domain expertise again on the model to mitigate the selection biases. Another use case is economic theory. You often know, for example, in an in a response scoring in marketing, where you try to predict demand as a function of the price, that usually for most goods there should be a negative price elasticity. So you should enforce that on your model, because if you don't, there may be noise and this may fluctuate and you may get nonsensical models for price sensitivity. So there are lots more use cases, and maybe in the QA session we can talk about some of them in more detail. Now to the new approach, where we combine the strengths of scorecards with tree ensemble models. So first, let me briefly explain what is a scorecard, because not everybody may be familiar with this. Scorecard is a simple table that assigns score weights to attributes or intervals of values for predictive variables. So if I come in as an applicant for credit, people look at my age, my marital status, my time at my employer, and so on, and depending on the values, I get sorted into one of these bins or intervals and get the score points, and then they get simply added up over all these predictive variables, and the end result is the total score. So you can see from this credit scorecard that, for example, young single divorced get very low points. They probably end up with a score that's pretty low, may end up below the cutoff, and they get declined. Whereas if you're older, if you're married, if you own a house, you may get higher score points. So these models are very easy to explain, but they are surprisingly flexible. So they are more flexible than a simple linear model, because you can model nonlinearities. Oh, I think I jumped one. You can model nonlinear dependencies between the score and the individual continuous predictors by means of stair functions that are data-driven. These scores are used for many things. As I said, not just credit scoring. We have them for response modeling or estimating future revenue. So the predicted variables can be binary, they can be continuous. We can use them for dimensionality reduction, for classification, and of course for decision making in conjunction with the cutoff. As I said, from a statistical perspective, they capture additive nonlinear relations. What they do not do is capturing interactions. So an interaction technically is if the effect of one variable on the score depends on the value of other variables. An example that we frequently see is that age interacts with many other predictors. For example, for young people, we may want to weight the effect of time on job on the score differently than for older people. Or for young people, it may be okay whether they rent or they own, may not make a big difference, but for older people, at least in the US, if they rent, they tend to be not as good credit risks. So the question is, if these scorecards don't capture interaction, we may leave some money on the table. We may not have the most predictive models yet. Typically, practitioners like to capture interactions by building segmented scorecard systems. For example, a separate scorecard for younger applicants and another scorecard for older applicants. That design captures interactions between age and all the predictors that are used in the scorecards. Obviously, the space of possible segmentations or partitions of the population is large. It's a combinatorial search space, and it's quite difficult to find good segmentations. So that's a problem we're going to address with our new approach. The second big advantage of Scorecard is that it's easy to impose domain expertise. So for example, if I believe, or if I want to follow the rule in the US that older applicants should not receive smaller score points, then I just impose linear inequality constraints between the score weights for these different age bands and enforce monotonicity in that way. The great thing is that it's easy to use industrial strength software for solving QPs or sequential QPs to achieve satisfaction of these constraints on the scorecard. Now, let me also briefly explore these algorithmic learning things. One prime example that we love to use at FICO is tree ensemble models. There are several variations: random forest, stochastic gradient boosting. Here I use a lot of stochastic gradient boosting. The idea is very simple. we built a single card tree, but to predict the y, the dependent variable in the observations, from a x, the independent variables. A single card tree, but we keep that tree relatively shallow, so it will only have a small number of leaves in a way that the tree will underfit the data. It will get some of the signal from the data, but not all of the signal. And then we look at the residual, and we build a second card tree, essentially, conceptually speaking, to predict the residual. But again, we built that tree very shallow, and then we build a third tree that predicts the residual of the first two trees. So it's kind of a sequential iterative algorithm where we add shallow trees to each other so that the residual gets smaller and smaller, and there is lots of interesting tricks involved in the algorithms like shrinkage. And in the end of the day, we get a series of trees or a forest that approximates this relation between x and y very, very well. And these models are excellent because they are not making any assumptions on the relationship between x and y. They can model highly nonlinear or interaction relationships. And so in that sense, we don't make any assumptions on customer behavior. Furthermore, these algorithms are fully automated. So it's more or less just a push of a button to learn these relations. The models, as I said, they don't make assumptions. They don't overfit much, so they are highly predictive. And you can even diagnose these models. They appear like black boxes, but you can diagnose them to gain really deep insights into the customer behavior and understand the nonlinearities and the interactions. On the downside, none of the parameters in these models has any real business interpretation. Unlike a scorecard, a score weight has a clear business interpretation. There are 10,000s of small parameters in these models. Each of these parameters has no interpretation. That's kind of the idea of algorithmic learning. You don't need to interpret these parameters in these models. All that matters is the predictive power. Now, as a corollary, you cannot impose business expertise into these models. You wouldn't know how to tweak these parameters. So they're very, very predictive models, but not immediately useful for business applications. Now, therefore, we have developed this two-stage approach. I think I have a problem here with the thing went dark. Sorry. So in the two-stage approach, we develop palatable segmented scorecards by a two-stage approach. In the first stage, we train a tree ensemble model, as I just explained. We score out the data set, thank you, and then we append the tree ensemble model score to our data set. It's called y hat. That's a tree ensemble model score. And then we can also diagnose and visualize the learned relationship. That's how we get deeper insights into customer behavior than we would get if we, for example, if we start with logistic regression modeling or discriminant analysis, kind of the more classical models that are simple, because they make strong assumptions. Here we don't make any assumptions. And then we can also use mathematical algorithms to analyze the interaction structure that's captured by these models. And from that, we will create a short list of segmentation candidates. As a reminder, segmentation candidates are variables that interact with many other variables. And then in the second stage, we grow a segmented scorecard tree to predict the tree ensemble model score from the X, from the predictors. So in this stage, we optimize the possibly constrained scorecards, imposing possibly these monotonicity constraints, if we choose so, to approximate the TEM score in the least square sense. So this is a thing we can do with quadratic programming. That creates, we also use from the tree ensemble model diagnosis the short list of segmentation candidates to guide the search for segmentation into promising directions. Because as I said, this space of possible segmentations is huge. We could use different variables to segment. Here the first segmentation is age. But then for each variable, we can also use different cut-off values for the segmentation. So we could split it at age equals 30 or 35 or 40. So we may try all the deciles of the age distribution for the best possible split. But we may have hundreds of variables in a realistic business problem, and the search space is still huge. Therefore, we use this short list of segmentation candidates that's proposed by the Tree Ensemble model. And then this algorithm is done in a greedy way. So we build a parent scorecard first, a single additive model, and then we try all kinds of splits and build children's scorecards. And then we look whether these children's scorecards have a better prediction in the least square sense on a validation set than the parent scorecard. If any of the children's scorecards succeed, we take the best of it, the best of the split candidates, and make it permanent. And then we apply that algorithm recursively. And at some point it will stop because I cannot improve in the least square sense on a validation sample anymore above the parent node. Now let me, for the final, the source is given at the bottom of the slide. So if you want to use your own favorite predictive model, you can also compare your results. We have 12 predictor candidates. It's a relatively small problem, small sample, 6,000 cases. About 20% of these cases are bad. The problem was to predict the probability of being good on a US home equity loan data set. So the first experiment I did is to develop 2 stochastic gradient boosting models. One of them additive, that's easy to achieve by restricting each of these shallow card trees to just having 2 children nodes. So it's kind of a stump tree. So that card tree cannot model interactions between variables. Therefore, the entire sequence of card trees that are summed up cannot model interactions. And that gives me a benchmark which is about AUC area, that's the area under the curve, area under the receiver operating curve of 0.93. And then I fit a model where I allow somewhat deeper card trees. They capture interactions. And the best model here I could find has about a 3% relative improvements above the additive model. So that gives me a good idea that interactions are pretty important in this problem. The next thing I said, we can diagnose predictive relationships. This is done by an algorithm also invented by the same person who invented stochastic gradient boosting, Jerry Friedman from Stanford. He also invented diagnosis area, and in a paper by Friedman and Popescu, we can learn about partial dependency plots. They're basically created by simulating the input-output relationship of that black box. That's a tree ensemble model. And here in this case, I just want you to concentrate on the red curve. That's the partial dependency between the debt-to-income ratio and the score. And as initially it's flat for debt-to-income ratio between 10% and say 40%, it's fairly flat, and then it rapidly deteriorates, leading to a lower score as you go above 40% debt-to-income ratio. But if you look more closely, you may, as a lender, a risk manager, you may get the concern that initially it increases a little bit between 10 and 30%, and that may be absolutely non-palatable because it could lead to reasons like I need to decline you because your debt-to-income ratio is too low. So to make this model really implementable, we have to tweak this relationship, and we can use scorecards to force these relationships to be monotonic. There are many more examples for the power of enforcing monotonicity. A second good feature of these tree ensemble models is that we can gain great insights in interactions. So for example, this is an interaction that's visibly clear between property value and debt-to-income ratio. And it takes a little usage to interpret these plots, but here we can see that property value matters less for your score if you have a large debt-to-income ratio. So that may be because if you have a debt-to-income ratio close to 50%, you're already such a bad risk that your property value doesn't really make a big difference. So finally, we can also get interesting and really useful summary diagnostics from these tree ensemble models. First one is variable importance. That tells us here that debt to income ratio is by far the most important variable for this problem. The reason for the loan is on the bottom. That's not very important. But more interesting for our application is that we can also get interaction test statistics. So for example, we can see that the debt to income ratio interacts with many other variables strongly. Also, value of the current property interacts strongly. And by rank ordering this list and picking kind of the top K, we can create a short list of segmentation candidates that will guide the search for the best scorecard segmentation. So with that, come to the performance comparison. So again, this shows a receiver operating curve, which essentially plots the true positive rate against the false positive rate as a function of the cutoff. And so the higher the curve, the better. The tree ensemble model wins, and this holds up under cross-validation. And so that's on a test set here. The tree ensemble model wins. The traditional scorecard development ends up with a single scorecard. There was no success in segmenting using a traditional approach to scorecard development. But with the two-stage approach, we get almost as close as the tree ensemble model, despite having imposed these monotonicity constraints that I was talking about. And that's a result we frequently find. Imposing these constraints does not necessarily cost a whole lot of performance, because there's this so-called flat maximum effect. You can create many, many models that predict about equally well, but some of the models are more palatable than others. So why not impose these constraints to make the models more palatable at a very limited loss of performance? So that's kind of almost free lunch here. Finally, the resulting segmented scorecard tree splits first at credit. That's the age of the oldest credit line, and then at property value. And these were all variables that interacted strongly, as the tree ensemble model showed. Quick check whether the constraint scorecards follow these constraints. Yes, they do. The constraint scorecard here has a monotonic behavior, monotonic decreasing. So it conforms with the reason code requirements. Finally, I want to discuss that in our experience, and we use this two-stage approach for a year now, it really accelerates the development of superior predictive scorecards by balancing the learning from data with the domain expertise. It's really a big time saver for businesses that are concerned about the deluge of big data, that they have to develop more and more models faster. Finally, thirdly, we can gain deep new insights into customer behavior by identifying interesting interactions. As I said, there are many other uses beyond credit scoring. Maybe we can talk more about those in the Q&A period. This approach scales very well to big data sets, so we use it for problems with 100, 200 variables and maybe 10 million observations, no problem. And in almost all the cases where we applied, we found substantial improvements over the traditionally developed scorecards. And that, even if it's just 1% improvement in area under the curve, translating that to millions of decisions can make a significant impact on the bottom line of these businesses. So with that, I thank you very much for your attention, and I want to open the floor for questions.